Okay, good afternoon, everyone. So before we start Sebastian's last lecture, I'd like to remind you that please sign on the registration sheet because we do need signatures for admin purposes. So that's the announcement, and please take it away, Sebastian.
All right. Let's get this started. So welcome to the last lecture. Before starting it properly, let me kind of summarize what we've done over the last 3 lectures. So in the first 2 lectures, we focused on infrared divergences, and then we've seen that at least in the case of QED, there was this magic cancellation between infrared divergences between real and virtual radiation, which was essentially guaranteed to us by the structure of unitarity cuts. And then in the following lecture yesterday, we focused on the ultraviolet divergences. And then hopefully I convinced you that at least at one loop, the structure of the running of the Wilsonian beta function, or more generally beta function, is actually also fixed by unitarity cuts. So you see from that structure, kind of a general pattern seems to be emerging, or at least a general pattern in this series of lectures, that everything is governed by unitarity cuts. And that's supposed to be a very practical tool because it tells you that, well, typically cuts are easier to compute than the full integral because you're just putting more and more delta functions. So this is supposed to be used as a practical tool that simplifies computations. And then what we're going to do today is, in a sense, finish the story of, well, at least finish the introduction to the story of the ultraviolet divergences. We talked about running in the first class yesterday, and today we're going to complete it with the story of matching. So the UV divergences are all about running and matching. Okay? So this is going to, luckily we've had wonderful lectures by Yara Shadmi on the story of on-shell methods in effective field theory. And in a sense, what I'm going to do today is build on top of those lectures and show you some cool stuff. And then we're also going to make a connection to the theory of dispersion relations, something that you've seen in the lectures of Aninda Sinha as well. Okay, so let's start. I'm going to start by explaining the story of matching and unitarity. So following the logic of the previous lectures, what we're going to do is, at first, I'm going to start very basic to make sure that everyone is on the same page. I'm sure many of you would have seen this type of story before. And then we're going to build on it and then move to more complicated structures that emphasize the role of unitarity in this whole game. Okay, so let me start by setting up some lingo. Okay, so we're going to have our favorite energy scale, and then I'm going to put a cutoff lambda. Cutoff lambda is going to distinguish my low energies from high energies. So this is low energies, also called IR, and then this is high energies, also called UV. Okay, so let's imagine that we have a full theory. What a full theory means is that we have a theory that we know across all energy scales. And now the goal of effective field theory, at least low energy effective field theory, is to understand what happens in this region if I integrate out or forget about the full theory. Okay, so let me remind you there's actually 2 ways to think about this problem. One is if you actually know the full theory in advance. So for example, if you have some guess for, say, beyond standard model physics, you write some theory and then you try to see what are the consequences of it on the effective field theory, and then how integrating out heavy modes is going to change the couplings in the EFT. So that's traditional approach. There's also a more nowadays fashionable topic in which instead of knowing the full theory, the only thing that you assume about it are some axioms, some general principles, locality, causality, unitarity, and things like that. And just based on those general axioms, you try to answer what are the possible EFTs that can emerge from the structure. Okay, so I wanted to highlight both types of approaches to EFT in these lectures. So we're going to move to that. And as you might anticipate from the previous lectures, what we're actually going to start doing is write some very basic toy model in which everything can be worked out. And then I'm going to illustrate some general principles based on this toy model. Okay, so let me consider the specific theory in which I have some low energy fields, lowercase phi, and then some high energy field or some massive field, capital phi. Let's say that it couples like this. Maybe I can write some more vertices, say this one. So here I'm assuming that the low energy field, lowercase phi, has a Z2 symmetry, and the other ones can couple to it with some couplings. Okay, so let me call this coupling here I of G1. Okay, because there's one heavy field coupling here. And then this one, let me call I of G2. And dot, there's going to be G3, G4, and so on. Okay, so what I'm going to do is I'm going to pretend that the light field is very light below the cutoff. In fact, it's going to be convenient to just start with the case of massless field. It doesn't get lighter than that. And then the mass of the capital phi, let me just call it capital M to simplify my life. And then I'm going to put capital M above the cutoff. So of course, what this means is that now we have some heavy field here sitting at some mass M. And then what we try to do is integrate it out and see what the effect of it is at low energy. Okay, so let me review some maybe before starting, just the dimensional analysis of the coupling constants. Okay, so this was already mentioned in the previous talks. If you try to study the mass dimension, the easiest is to remember that the scattering amplitude with n external particles has the mass dimension 4 minus n. And what this means is that this contribution, you can pretend that this is a contribution to a free particle amplitude. So it means that this has to have mass dimension 1, this has to have mass dimension 0, and so on and so on. Okay? So one way I can implement that is that I'm going to write G hat for a dimensionless quantity. And then what I can do is I can use capital lambda, which is my natural energy scale. I can use that to set the units. Okay, so if I work it out, then the dimension is 2 minus k in this case. Okay, so this is what I said. If k is equal to 2, then this is dimensionless, for example. Okay, so the lingo here is that the G equals 1 is called the relevant coupling. G equals 2 is called marginal. And Gk greater than 2 is called irrelevant, which is the reason why I didn't write it. Okay, so how many of you have seen this stuff before? Okay, one. Okay, good. So let me emphasize this is dimensionless in my notation. So now, if we wanted to talk about effective field theory from the on-shell perspective, I have to agree on some kinematics. Okay, so I'm going to study the kinematics. We can just focus on the case of 2-to-2 scattering, which is the simplest interesting case. In this case, we have the kinematic invariants S, T, and U. We call that one of them always has to be positive and the other ones have to be negative. So let me take the absolute values. If I want it to be in the EFT regime, it means that all the kinematic invariants have to live in this low energy theory. So that means that they have to be way below the cutoff, so below lambda squared. Okay, and then likewise, I've put the mass of the heavy particle to be above lambda. Okay, so now what I can do is write the tree-level amplitude. For the full theory, so let me call it M full phi phi phi. Okay, and this is very easy. I only have 3 diagrams in which I have the exchange of the heavy field in the S, T, and the U channels. Okay, so this can be written as minus G1 squared S minus M squared and permutations. This. Okay, and then I can also pull out I can substitute this dimensionless quantity here just to make sure I'm having my powers right. Okay, so I get the lambda squared everywhere. And then next, if I really wanted to go from the full theory to the EFT, the only thing that I have to do is apply this kinematics. Okay, which means that I have to just Taylor expand the amplitude. So at tree level, that's super easy. I'm just gonna expand it by pretending that this separation of scales is correct. So what this gives me is plus 3 G1 squared lambda squared divided by mass squared to leading order, and the subleading orders are going to be G1 hat lambda squared. And then a bunch of terms, let me call it I. In fact, infinite number of terms that look like Si, T to the I, and U to the I with this mass dimension. Okay. So this is hopefully quite simple. Here I'm missing the term I is equal to 1. And the only reason for that is that this would give me S plus T plus U, which vanishes by momentum conservation. Okay, so now from this perspective, now I mean the EFT, this coupling here is what I would call the effective coupling. In fact, it's the effective phi to the 4 coupling. Or in other words, Wilson coefficient in the lingo that you must have heard in the previous days. So just to emphasize the point here that the way that I should think about my effective coupling is that this is approximately the effect of scattering this heavy field. But if the heavy field is really very heavy, then this means, oh my God, U channel here. Okay, then this means that the intermediate particle with the heavy mass, it cannot propagate very far, right? It's contained to some local region of space, and what this means is that effectively it approximates a quarter coupling, and this is the interpretation of this formula. Okay, so this is hopefully has been very basic, and now what we're going to do is we're going to reformulate this kind of exercise in a way that makes manifest the connection to analyticity and to unitarity. So let me start doing that by giving you a more general expansion. So I'm going to write an expansion for the EFT again, for 4 scalars. I should probably emphasize that in general, if you go from full theory to EFT, in principle, studying effective field theory also carries with its nature the reorganization of the degrees of freedom. It just so happened, so that would mean that the phi in the high energy is really different from the phi in the low energy. But it so happens that in this case, everything is so simple. Let me just call phi on both sides, in the EFT, in the full theory, the same phi. Okay, just a scalar. So let me write a general ansatz for this amplitude. So by general, I'm going to consider the scalar case. I'm going to consider a tree level. And I'm going to use both symmetry. Okay, and if I do that, the most general amplitude I can write down. So both symmetry means permutation invariance under exchange of any pair of particles. Okay, so I can write it in terms of some coefficients. Let me call them h with a subscript. Okay, this is the first term that I can have. If the theory was cubic, then I can have h0, which would be the quartic coupling. And once again, I'm going to skip the h1 because it vanishes by momentum conservation. I can have h2, h3, and so on and so on. Okay, so in our original EFT, the specific instance, this is a general parameterization. This was a specific instance of the effective field theory. In this case, so our EFT, what we had is that h of -1 was 0, right? There was no cubic term. Then h0 was 3 times g divided by m squared. And then h2 was something like this, and so on and so on. All right? Excellent. So now what I'm going to do is I'm going to reformulate a little bit the type of expansions that we had here with the grand goal of including loop corrections. Yes?
Sorry, what is, again, the idea of doing this kind of ansatz? Why do we have this?
So the question is, what is the idea about building this kind of ansatz? So this is the general philosophy of effective field theory that well, in the traditional formulation of effective field theories, you would write down the Lagrangian with all possible couplings that are consistent with all the symmetries that you impose on the problem. This is just the amplitudes version of that, in which you just write the most general ansatz for the amplitude, provided that it's scalar, tree level, and both symmetric. And then what the idea is that any full theory in the low energy approximation has to look like this, with some specific values of these couplings. So we've seen an example of that in which the values of the couplings have been these ones.
I mean, my question was like, how both these symmetries from this and this. So why, for example, I don't have like a term like STU or...
Oh yeah, okay, excellent. So this is actually sorry, the question was, why don't we have different terms? So this is one exercise. I guess maybe one question was about STU. Okay, clearly I can write STU. But one exercise is that if I use momentum conservation, so write U as -s minus t, it actually is the same as this term in here up to a number. Okay, so this is to say that the things that I've written here are entirely exhaustive because including this term would just shift the coupling. Good? All right, any other questions? Okay, so now we're going to include loop effects. And there's a naive way of including loop effects, which would be just to write down all Feynman diagrams, say at one loop, that contribute to the full theory, computing those diagrams and then expanding them in this limit. And this would certainly work. And this is how we usually do this computation. But what I wanted to convince you of today is that there's a better way of thinking about it. And that better way will be using dispersion relations. So at the beginning, it might look like I'm just doing something very weird and complicated. And at tree level, it will be, in fact, like a sledgehammer tool to do something that we could have done using Taylor expansion. But we'll see that it's actually a powerful tool when it comes to generalizations to loops. OK, so what I'm going to do is first rescale all Mandelstam invariants. With some parameter z. So I'm going to have my s, t, and u. What I'm saying here works at any multiplicity. So you could have, this could have been any other Mandelstam invariant. And I'm going to rescale it to a new variable, s hat, t hat, and u hat, which is simply z times the original s, z times the original t, and z times the original u. Okay, with the idea that z controls the scale at which I'm measuring, at which I'm probing my my physics. Okay, so let me actually move to a different blackboard now. Okay, so you must have seen this trick before. You have your scattering amplitude. What I do on it is I'm going to implement some shift with some new variable, typically called z, which is foreshadowing the fact that z can be complex. And then I'm going to play some complex analysis games with the z. All right, so hopefully this is familiar from things like BCW recursion relations and other recursion relations. Okay, so what I'm going to do is I'm going to draw a complex plane of z. In fact, I'm going to draw it twice. Okay, there's going to be two complex planes because I'm going to study the effective field theory. So M, EFT, and I'm going to study the full theory. Okay, and then I'm going to compare the two. So the if I look at the ansatz in the effective field theory, it's actually very simple. If I look at the, oops, maybe I should keep this here. If I look at this shift and I apply this shift to my ansatz in here, you see that the only thing that can happen is that it's going to be 1 over z, z to the 0, z to the second power, z to the third power, and so on. So the analytic structure of that is very simple. The only thing I have is a pole at z equals 0. All right? Now, on the other hand, let me repeat the same analysis for the full amplitude. Okay, so maybe let's first plunk down the types of diagrams that we've already analyzed. Okay, so there's going to be these kind of expressions here. So after the shift, I'm going to get z times s minus m squared, z times t, z times u, and so on. So if I'm going to look at where they are located, there are going to be some poles. In this case, 3 simple poles, because we have 3 Feynman diagrams that are going to be located at m squared over s, m squared over t, m squared over u. All right? So maybe I should draw a little diagram here to emphasize this comes from the, say, S-channel exchange, like this. All right? But now I promised that I wanted to go beyond the tree level. So I wanted to start including loop effects as well. So what is the simplest loop contribution to this 4 external massless scalars? Well, it's going to be some bubble in which I exchange, hopefully you can see this, within the bubble, I'm going to exchange two heavy fields. Okay? So when is this first allowed? This bubble is first allowed, it's going to give me a branch cut that is going to start at the place where the phase space for the production of two massive particles opens up. That phase space opens up when the energy is equal to 4m squared over s, or rather when s is equal to 4m squared. Okay, this is just when there's enough energy to create these two particles. And then likewise, there's going to be similar cuts here going to the left, responsible for the T channel bubble, the U channel bubble, and so on. All right. So the analytic structure of my full amplitude in the complex Z plane is looking something like this. And of course, if I start adding more loop corrections, there's going to be more cuts opening up at different positions, and so on and so on. All right, any questions about this? Okay, so yeah. Can you repeat, please?
If the branch cord needs to be only direction.
I see. The question is about whether the branch cut has to be on the real axis, and then the answer is yes. You can prove that the cuts will always organize. There could be very complicated cut structures starting at 2 and higher loops. There could be multiple thresholds. There could be anomalous thresholds and stuff like that. But they're guaranteed. I can tell you after the lecture how we would prove this. They're guaranteed to be on the real axis and always go either to the right or to the left. Okay, excellent question. Oh, and then I should have probably emphasized what I'm doing here is I'm using the kinematics in which S is positive, and then T and U are negative. Okay, so this is the reason why these things are involving T and U are to the left, and the ones involving S are to the right. Okay, so now what I can impose, well, what I've drawn here is really two separate pictures. And at the face of it, they don't have much to do with each other. But now we want to marry them together. And the way that we do it is by imposing a matching condition. Yes?
Why are we guaranteed to only have still a simple closed structure, or don't have to?
So the question is excellent. So the question was, if we start including more loop effects, do we not have to include more complicated analytic structure on the EFT side? Is that the question? The answer is yes. In principle, yes. This actually depends on the theory. So what I'm doing from this perspective is I'm going to do tree-level effective field theory. But what you can do is you can include one loop corrections on top of that as well. And this will indeed include, could include more complicated structures. Yeah. So what we're doing today is one loop to tree level, which is the classic story. Then you can upgrade this in principle if you want. Okay. So the matching condition is going to tell me that I'm going to impose that the full amplitude at some chosen value of z is going to be equal to the EFT amplitude. Okay, so where do I have to impose the matching? Well, I guess I erased the separation of scales, but it's kind of obvious that where I have to match below the scale at which I have some new physics entering. Okay, so this is what I called capital delta in there. So you can imagine that there's a circle that encloses all the low energy stuff, but none of the high energy stuff. Okay, so that circle here is absolute value of z is equal to some delta. It's up to me how I choose the delta, as long as it's below the cutoff. Okay, and then what I impose is simply this equation, that this equation is true for z is equal to delta. Okay, let me actually rewrite. So these are rather bulky expressions that we've included for the EFT side. Let me just rewrite it slightly to emphasize the z dependence. What I mentioned before is that we can have 1 over z, then we can have a constant piece, and then 2z squared, and so on and so on. Okay, so these m's are some combinations of the h's on the other blackboard. Okay. So now, from this perspective, the story about matching is all about extracting the m's or extracting the h's. I'm going to loosely refer to them as the Wilson coefficients. Let me write it here. Okay. So how do I extract the, say, Kf coefficient? Okay. Well, that has a very suggestive answer. Once I see, again, once I see a thing like that and I think about contours and so on, of course, I want to extract it by a residue theorem. Okay, so I'm going to perform a residue around z equals 0, dz, and then I have my EFT amplitude as a function of z. And then if I adjust this denominator here to z to the k plus 1, then you can see if I hit that, if I apply this formula here to this expansion, then I get the Kf coefficient. Actually, what I wanted to do, strictly speaking, is z equals delta. Thank you. Okay, so from that perspective, what I'm doing is I'm doing an integral like this, okay, which of course I can close up to be a residue around 0, and then I have my formula. Okay, so that's very cool, because now what I can do is I can impose my matching condition. Okay, I'm just going to impose that EFT is M full. So what this means is that this is teleporting me essentially to this blackboard. Okay, and then on this blackboard, what can I do? Well, in principle, there's going to be some coefficients here. So since this blackboard was supposed to be the full theory, including the UV, what I'm going to do is expand it out. Okay, so this contour, let me actually correct it straight away. I'm going to expand it so that it encloses this residue, this cut, this residue, and so on. Okay, and I can be slightly careful about the orientation. Okay, hopefully this is readable. Okay, so very schematically, what I've written here, I'm going to write a more explicit formula in a second, is that the Kf EFT coefficient can be expanded in terms of these residues and these cuts. So let me just write it as residues plus discontinuities. Okay, I actually forgot about something. Maybe there's a, yes? The question is there a singularity at z equals 0? So I could have closed it up at z equals 0, but I know that within this contour, this side and this side are the same, so I would get like 1 equals 1 identity, so that would not be very useful. This is if I shrunk it inwards, so instead what I'm doing is shrinking it outwards, or expanding it outwards. Yeah? Yeah. Oh yes, that's only because, yeah, excellent. So the question was, it does not look like the formula for the M4 has this singularity or the origin, but I'm actually adding a crap ton of them in here. Okay, so they're there. Okay, there's actually something I missed in these equations. Maybe there's going to be a question that someone's going to point out that. Sorry. Yes, someone's going to point out that I forgot about the contribution from infinity, which has this orientation. Okay, so let me actually write it here, plus residue at infinity. Okay, so I'm going to come back to the residue at infinity in a second. Okay, let me write that this step to this step was deforming the contour. Okay, and let me also give a name to this relation. This relation is, in a sense, the version of what you've seen in the lectures on dispersion relations. Is a specific type of dispersion relation. So if I look at what I've been doing here is I've been rescaling all the energies of all the particles at the same rate, while keeping the ratios of the Mandelstam invariants the same. Okay, so physically what this corresponds to is that the angles stay the same, but the energies grow. So this is what you can call a fixed angle dispersion relation. Okay, so fixed angle dispersion relation is what we need from the EFT perspective, because we want to relate low to high energies. Okay, so now let me tell you about one fact about discontinuities. Let me just say it like this. It's a fact that you can prove that if I compute the discontinuity, maybe I should ask before that, how many of you know what the discontinuity is? Yes, exactly. So the discontinuity is the difference in this context between the value of the function above the cut and below the cut. Okay? So in principle, I can actually compute two types of discontinuities. Let me write it like this. So either discontinuity across the positive axis or the negative axis. The reason why I wanted to distinguish between the two of them is that, well, both of them are related to the imaginary part. In fact, 2i in my conventions times the imaginary part of the full amplitude at z. The only distinction is that the one across the positive axis is going to be plus, but the one along the negative axis is going to be minus. This has to do with the fact that it's related to the I epsilon prescription. It's related to the fact that if you wanted to, the moment you have a cut, you have to make sure that you approach the cut from the physical side. Physical side is important to preserve causality conditions. And it turns out that on the right axis, you're supposed to always approach it from the above, but on the left side of the axis, you're supposed to approach it from below. So that distinction is reflected in the plus-minus sign when you relate the discontinuities to the imaginary parts. Okay, so now what's so exciting about writing the discontinuity as the imaginary part? Well, we've seen this in the previous lectures. The imaginary part is it's fixed by unitarity. Once again. So essentially, if we combine all the ingredients that we've seen today, then what we're getting is a relation between Wilson coefficients in the EFT through the dispersion relation to the imaginary part of the full amplitude, which in turn is computed in terms of cuts. So let me write down an explicit formula, yes?
So at this point, we assume the unitarity as just pure assumption, right?
Yeah, the question was whether we assume unitarity or whether it's an outcome. Yeah, okay, so I got excited about writing the imaginary part of the full amplitude precisely because I'm going to assume that the full amplitude satisfies the unitarity. And that means that I can write the imaginary part in terms of using the generalized optical theorem in terms of the cuts. So yes, I'm assuming unitarity for the full theory.
But this is assumption.
Yes, it's an assumption. Yeah. Any other clarifications? Okay, so let me maybe write a concise form of the dispersion relations. Then I'm going to do some examples, and then I'm going to move to positivity. Okay, so the concise version of the dispersion relations is that MK can be written as the 1 over pi. So that's the pi from there. So I'm just going to plug in this expression into here, right? So the pi I is going to cancel out. Sorry, 2i is going to cancel out. I have pi. And then I have integral from some cutoff delta to infinity minus the integral from minus infinity to minus delta. And both of those are dz z to the k plus 1. And then the imaginary part of the full amplitude at z. The only potential sticking point could be this issue with the residue at infinity. But it turns out that you can actually do this analysis if you do it diagram by diagram in perturbation theory. What happens is that the z dependence at asymptotic z is very simple. So my integral is going to look like z to some power. Okay, and I have to do a contour integral over z. So you perhaps know that if I have an integral of this type, which is called a scaleless integral, then it integrates to 0 in the rank. Okay, and that's because the contribution at infinity is scaleless, z. Okay, so this closes the loophole. Now everything is determined in terms of the imaginary parts. Maybe a little convincing would show that the residue can be also written as the imaginary part of a pole. Okay, so at this stage, let me do some examples. So first of all, let's reproduce the tree-level example. So as I mentioned before, in the case of the tree level, applying this technology is really a vast overkill. But nevertheless, it's going to be comforting to recover the result that we've seen before in a different way. Okay, so let me do the first example. We're going to have the contribution from the T-channel diagram. Now, if I wanted to plug it into here, what I have to do is compute the imaginary part, which is the cut in here. Okay, so I'm going to call it the imaginary part of the S exchange, S channel exchange. This is the imaginary part of minus G1 squared divided by S minus M squared. And then here I should not forget about the I epsilon. Okay. Now we can use everyone's favorite identity. I believe the Sikorsky-Plemole identity, which tells me that the imaginary part of an object that looks like this is equal to a delta function up to some constants. Okay, so the cut of the S-channel diagram looks like this. And now, if I wanted to compute the contribution, so I'm going to call it delta mk. So this is going to be the shift in the K Wilson coefficient due to this specific diagram. Well, what I have to do is plug in this formula in here into this equation. And now this equation is going to be super simple because I have an integral of z with a delta function. Okay, so this is going to be G1 squared, then integral from delta to infinity, dz z to the k plus 1. Now a delta function, I need to apply the shift. So this is really zs minus m squared. Now I can localize the integral on the delta function. And the result of that is G1 squared s to the k, if I compute the Jacobian from the delta function, divided by m to the 2k plus 2. Okay, which is the result that we've seen before. Okay, so that's not super impressive. So let's move on to the juice of why we started talking about this. Which, as I mentioned, the idea was to avoid computing difficult integrals. And this is something that you would have to do in the traditional EFT approach to computing this contribution. Okay, you would just have to sit down and compute this one. It's actually not super complicated. It's going to give you some logs and stuff. But you can actually do it with much less effort. Okay, so the imaginary part of the bubble is going to be, so there were two couplings. I call them G2 and G2. So G2 squared. Then I'm going to include some normalization factors from the phase space. These are the same ones that we've seen yesterday in the talk on the renormalization. And in fact, the integral is almost exactly the same. There's a delta function. The only difference is now I insisted on including the mass. So I have two delta functions. Okay, so I have to compute this integral. Perhaps I don't need to convince you that this integral is much simpler to do than the full Feynman integral. And maybe even someone knows the answer to this. You do? Okay, so that's a good start. So in the massless case, it was pi over 2. That's correct in the massless case. And now there's going to be a tiny correction because we're doing a massive case. Well, we can almost guess it because we know that this contribution has to open up. The imaginary part has to be allowed whenever there's enough energy to produce the intermediate particles. So this means that this has to be proportional to the s minus 4m squared, right? That's just from kinematics. And then we also know that there has to be a branch cut starting at this point. And do you know what is it, a log or is it a square root or? You can vote. Okay, it's a square root. Okay. What is suspense? Okay, so the final answer after doing a little, change of variables to spherical coordinates and so on is this one. And indeed, in the massless limit, it gives me pi/2 that you remembered from yesterday. Okay, so now this was the first step, computing the cut, which in this case was fairly simple. And then the second step, rather, is computing the contribution to the cave Wilson coefficient from this bubble. Okay, so let me write the formula. So this is going to be G2 squared, and then if I work out all the factors, just copy them from notes, you get this integral. So you have to integrate over all allowed region from 4m squared to infinity, and then dz over z to the k plus 1. And then I just copy this, right? So this is zs minus 4m squared and zs. Okay, this is a fairly simple integral. You can do it. In fact, in a sense, you've seen this integral many times over the last week. After a small change of variables, this gives you something like the beta function. Okay, if you write it down, it's equal to G2 squared over 32, and then S to the mk, m squared to the k, gamma k plus 1, divided by gamma 2k plus 2. Okay. Do you have any question about the result? Okay, certainly you would have a question about this result if you started plugging in different values of k. So if you plug in k equals 1, k equals 2, 3, and so on, it's okay. So this is valid for k being positive. There's, however, a small problem when k is equal to 0. And that's because the gamma function has a pole at k equals 0. So strictly speaking, this computation was not valid in the special case when k equals to 0. And it's easy to understand why. It's because this integral is actually divergent, right? So that means that in the special case of k equals 0, you need to use dimreg, and this for a good reason. And then if you computed this in dimreg, you would get something like 1 over epsilon plus a log, and so on. Something like that. Okay. And this emphasizes the interplay between the matching procedure, which is what we're doing here, and running. So in principle, on top of the matching, we also have to do the running because we have the 1 over epsilon, so you need to renormalize it. Okay, so this is running. Okay. So this completes the story of what I wanted to tell you, at least at one loop, about the matching procedure. The bottom line is that the matching by computing the full integral and then expanding is doing way too much work, and hopefully I convinced you that there is a slimmer computation that you can do, which instead is using unitarity techniques. And what I wanted to do in the last 7 minutes is make a connection between, make a connection between this approach and the positivity bounds, because we're almost there. And I think positivity bounds have been mentioned at least a couple of times this week. So I thought it would be nice to actually see how they're derived from this perspective. Okay, so the basic idea is that, well, in principle, what we've done here is we've had a specific model in mind, so we knew how the high energy theory looks like. And then what we've done is we've done a computation, and then in the end, we found some coefficients here. And one thing that you might notice about these coefficients is that they're all positive. And then one thing that you can ask is this always the case? If you play this game with many other theories, with different particle contents, fermions, and so on, you would very quickly discover that many of the Wilson coefficients are always positive. And this turns out to not be an accident. In fact, it's implied by general principles. So what we're going to do is we're going to study this dispersion relation that is written here in pictures in the forward limit. So in the forward limit, what I mean by that is that the t is going to be equal to 0. And strictly speaking, there's some problems when there's a massless pole. So I'm going to pretend that I'm going to just, since we only have 5 minutes now, I'm just going to kill all the t-channel poles for this purpose. Okay, so from this perspective, the dispersion relation in Z is going to simplify. And the reason why it's going to simplify is that when t is equal to 0, then u is equal to minus s. Maybe I should write it here. T equals 0 implies that u is equal to minus s. So there's a certain symmetry that now our diagram acquires. And that symmetry is the left-right symmetry. Okay, so whenever, for example, here I had a cut at 4m squared over s, I have a sister cut, which is at 4m squared over u, but now u is equal to minus s, so this is minus 4m squared over s. Okay, so there's a left-right symmetry, and similar for other kinds of cuts. Okay, so now the question is, how do I exploit symmetry? And you do it as follows. So maybe let me first write down, there's a symmetry under Z goes to minus Z. Okay, so what this means is that if I write down my formula for MK, this is going to be 1 over pi, and then the integral from delta to infinity minus the integral from minus infinity to minus delta. This with the imaginary part. Strictly speaking, in this story, I actually need to be slightly more careful about the terms at infinity. And the reason for that is actually related to what we've studied, was it yesterday or 2 days ago, about the Froissart bound. Froissart bound told us that the cross section decays as grows as a log squared of the kinematic invariant. So what this means is that if you relate it to the scattering amplitude, it means that it grows as s times log squared s. Okay, so what this means in the language of subtractions is that you need to kill the terms at infinity. You actually need at least 2 subtractions. Okay, so this terms vanishes now in the forward limit only if k is at least 2. Okay, so you need at least 2 subtractions. Okay, so in any case, in this case, I have, if I use the symmetry under z goes to minus z, you see I can apply the symmetry on this integral. The integration boundaries are going to shift to the integration boundaries that I have here, just because of the left-right mirror symmetry of this diagram. Okay, and then if you also work out the powers of the minus signs that you get from one side to the other, you would find that to go from here to here, we're going to pick up -1 to the k times the original integral. Okay, so what this means is that if k is odd, then the two of them are just going to cancel out. And if k is, so the Wilson coefficient is going to be 0. And if k is equal to even, then they're going to double up. Okay, so what does it mean? I'm going to get 2 divided by pi and the same integral. Okay, so this is if k is even and at least 2. I can write this identity. And now what you can notice is that here I have the imaginary part of my amplitude. And the imaginary part is related to the cross-section. And the cross-section always has to be positive. So this means that this, strictly speaking, non-negative. So what this means is that this function here is non-negative. And I integrate it over the positive, with some positive weight of 2 and pi. So what this means is that the full mk has to be positive as well. Okay, so the outcome of this discussion is that mk has to be non-negative for k even. Okay, and this is basically the mechanism behind, the simplest mechanism behind the positivity bounds. As I said before, you could have had a lot of fun with different EFTs and computed these Wilson coefficients. In the end, you would discover that all of those that are listed here are positive. And what we've seen in this part of the lecture is that this would not be an accident. It's in fact a combination of these axioms of quantum field theory. We've assumed that the amplitude was analytic, and then it was unitary at high energy. And as a consequence of that, we found that for the EFT to be consistent with those principles, certain Wilson coefficients have to be positive. All right, this is the beginning of a very fun story in which you can bound using more complicated arguments. You can actually bound these coefficients from left and right and study the spaces of effective field theories. We don't have time to discuss that, so let me just wrap it up here. And yeah, thank you for your attention. What's the question?
How are we sure that imaginary part of matrix element C equal imaginary part of matrix element minus C?
So the question is, how are we sure that the imaginary part, how are we sure that the imaginary part of the matrix element with Z and plus Z and minus Z are the same? Yeah, this follows from the Bose symmetry, or in this case, the SU symmetry. So it's actually, in this case, it was very important to have in mind this thing that I mentioned half an hour ago, that from this axis, you're supposed to approach the correct side from the up side, but here you're supposed to do it from the down side. And this guarantees that the imaginary parts are the same, not minus of each other. And this is exactly how the mirror symmetry works in this case. Great question. Yeah. Yeah.
When is the real part?
Yeah, excellent question. So the question was about we've used the imaginary part left and right, but what about the real part? So in a sense, the real part, using similar techniques, the general kind of theory of complex functions tells you that the real part is not independent of the imaginary part. So if you know the imaginary part, you also know the real part. And this can be proven by this kind of playing around with dispersion relations. In fact, this is where the dispersion relations originate to relate the real part of the amplitude as the integral of the imaginary part and vice versa. This dates back to the many centuries ago. So maybe that's the answer to this, that the real part, in a sense, it's already determined in terms of the imaginary part. But more crucially for us, the imaginary part is relevant because it's the one that participates in the cuts. So, and there's no simple enough statement that you can make along those lines that you can make about part. Excuse me? This is true at all loops. In fact, it's a non-perturbative statement. It follows from S dagger S is equal to 1, essentially.
Are there any more questions? If there are no more urgent questions, then let's thank Sebastian again for very nice lectures. Okay.